say a lot of it. I think it did. It is. Now it makes sense more like an ET reference. ET is. You didn't remember that reference? Well, I did suspect that, but I just kind of thought they just went with the gag of bicycle Gruyere like that. But now when you say it out loud, Gene Dave phone calling, ET goes home. It's ET goes home. That does. I think they made the reference even more intentional. But so it's your favorite part. What part do you think? So Arthur kind of takes the role of Kenny in this series. Yeah, but there is an episode where he tries to prevent all of his deaths throughout the series. One of my favorites was when he prevented his death from Saberline. Did you hear what I said? You know, who helped him realize his vision of death and help him kind of help support him in preventing his death? Send haiku. Send haiku if ever alive.
We heard about those guys. I was talking about this all the time.
All right-handed. You're talking about right?
I don't know the world. I was in this world. Here's a word. Look at that. Here's a word. It's actually really good. Apparently only
really easy. What? It doesn't ruin the game. It makes it possible.
Which game?
No.
Oh, nice.
There's some like games that look similar to it now. Or like
So,
on Tuesday. What game was that? In class. Oh, that's I tried to 10 minutes.
So I wanted to say a couple things about the homework that was due Tuesday. There were really two things. One is a few people kind of saw this expression here as in show all solutions in this interval. And, or maybe they missed it. This kind of implies that the question, they wanted it in radians, but I didn't really care about that. You gave me degrees or radians, it was fine. But, you know, if I gave you a problem like sine inverse of 0.5 in this range, you'd have two solutions. Generally, you know, for this one you would. I mean, you have a sine function, right? You're always going to get, you know, no matter where you draw the line, you're going to get, well, no matter where. two different solutions. If you draw it just, I guess you can get, if you draw it here, you can only get one solution. If you draw it here, you get no solutions. But generally, there are two solutions. So keep that in mind. You know, if you get a quiz problem and it says in the interval 0 to 2 pi, that means there's probably going to be two solutions. Or if not, there's going to be a reason. The other problem that after I looked at it closely, I thought, I don't really want to confuse people this way. This is notation, and the book makes a distinction here, which I don't like at all. Definitely this is what we've talked about. This is the square of cosine pi over 5. As far as I'm concerned, this is the same thing, even though that's clearly not what the book wanted. What the book wants is this, and I think their notation is terrible. I mean, to me, parentheses are an indicator of what the argument is. And if you want the argument squared, you have to square the argument. But nevertheless, you know, I didn't really care what you said here. You could say it either way. I thought it was fine. For some strange reason, you know, I only got like about a dozen papers, but at least a third of them, I think, were in the wrong mode when they did it. Because they got totally weird numbers. So, okay, so that's what I wanted to say about the homework.
So, now that you disagree with the book on notation, for the purposes of the quiz or midterm,
I won't do this.
you won't do that.
I won't do that.
Okay.
I mean, that's to me just stupid. If I meant this, I would do this. I mean, I put the problem on there just because the book thought it was important enough to have a little sidebar saying, watch out for this, and then they do it this goofy way. So anyway, okay. So that's that issue. There's another issue which we didn't really cover Tuesday, but I thought is important. It has to do with one of the, or two of the identities, specifically sine of, oh, you know, before we do this, I might as well get this out. I made up a sheet of, I think, all the identities we've covered here. I suggest you not take a paper airplane out of this, because you can bring this to the quiz or to the final, and if you want, you could write on the back of it, or you could. Bring in your own sheet or card or whatever. A lot here.
That is,
Thank you.
This would be a good study guide to go on.
Well, I'm going to give you probably Tuesday something a little more study guide-ish. There's a quiz on Tuesday, but there's a final exam the following Tuesday.
I remember there was
It's
Sorry, I missed you.
Which symbol is the one with the line?
Symbol?
Is that a zero value set? The one's not there. It is the same. Yeah, the one that's not there. What
The other O.
V.
Fee.
That's it.
Yeah, it's a
Five.
I
Oh,
don't know, variable.
Yeah, that's right.
Too warm for this. too cold not to have it. Apparently it's too cold not to have it. Okay, so where was I? I wanted to show you these, there were these two identities, the half-angle identities, where somehow the identity ends up with a plus or minus in front of it. Oh. And that plus or minus doesn't mean what you might incorrectly think it means. It doesn't mean both of those answers are correct. It means it could be plus or it could be minus. So let's look at a real simple example. So if I were to say, you know, if I were to say, what is the sine of 15 degrees? Something exactly. Something, don't know off the top of our heads. So you immediately identify this as something we can treat as 30 degrees over 2. And so now we have an identity that's going to tell us that this is plus or minus the square root of 1 minus the cosine of 30 degrees over 2. Okay, cosine of 30 degrees is what? 2. Let's leave that in there as long as we need it. And so simplifying a little here, we have what? 1/2 minus the square root of 3 over 4. So square root of 3 is about, I'm not reducing this at this point. I mean, this may have some better looking appearance somehow. 2 minus square root of 3 over 4, that looks better. Square root of 3 is about 1.7, so it's about 0.34. Okay, whatever. Question is, what is this plus or minus thing here? Well, we know in this case 30 degrees is here, and so 15 degrees is here. What quadrant is this in? It's obviously the first quadrant. So obviously, it's not plus or minus, it's plus. So if you were given a problem like this, you would have to use some kind of reasonability test here and say, well, which one is it? Is it in the first quadrant, in the second, third, or fourth, to tell you whether it's a plus or minus. Okay. Okay. The next thing on the agenda is, I think, we'll see how many people took me up on it. I suggested that you take a look at homework that's due next Tuesday and see if you have any questions on it. That's section, I think, mostly section 10.3.
10.2 and 10.3.
Oh, 10.2 and 10.3. Are there any questions on any of those problems? They're not due yet, but there's something. Even if you have your book, you can even take a look and glance through the problems in the back.
Would this be on chapters 10? 1, 2, 3?
Pretty much 10, yeah. 10.1.
You're doing any
I guess I'm just gonna have to find something to throw up here just to
Grow up.
see if people have any idea here what's going on.
We can grow up.
So, where's the problem? Do sine x, this is a solving equation problem. So sine x equals 0.7. Anybody have any idea how we might go about that? That actually wouldn't be a good idea. Would not be a good idea. There's a, I mean, you could. Have to think about what to do next. So here's where maybe spending a little, an afternoon with this sheet might come in handy. Does this look like anything on the sheet? Yeah, it's like sine 2 theta, or in this case I'm using x. Oh, well that's different, isn't it? I'm going to put this up here so we can, I want to know the solutions to this from 0 to 2 pi. So, first thing I could do is I could find out what the inverse sine of 0.7 is, couldn't I? I'm gonna do it in radians instead of what the problem seems to want. Okay, so I get the inverse sine of 0.7 equal to 0.77, we'll say 5. This is in radian measures. Which is equal to what? It's equal to 2x. But before I go on and deal with that, well, 0.775 is definitely in this range. But where else will the sine be in that range?
First and second quadrant.
Yeah, okay, so this is the first quadrant. What does the second quadrant solution look like? Okay, again, always, if you get hung up on a quiz, something like this, it's always a good idea to draw that little diagram here.
Pi minus 0.775? Pi minus 0.775?
Yeah, so this is the 0.775. And then here, the same angle up from here is going to be what? It's going to be pi, or 180 degrees, minus 775. Okay, so I'll leave it like this for the moment. And now what do I do? Okay. I'm drawing a blank, I guess it's not real clear. Each of these is equal to 2x. So how would I get the answer I'm looking for?
Isolate the x.
Yeah, and how would I do that?
Divide by 2.
Divide by 2, yeah, okay. So this divided by 2, and this divided by 2. Those are solutions. Now, a good question right now would be, are those the only solutions?
Are those the only solutions?
Between 0 and 5?
Yeah.
Say yes. But it seems like
Commit yourself.
yeah, because when you ask these questions, usually it's some sort of.
You know, it's like take a coin, heads you pass, tails you lose. It's 50-50 chance.
But your equal signs aren't true anymore.
My equal signs. Which equal sign?
So you just divided by 2, but you got to erase that.
Oh, yeah, okay, yeah, thank you. Okay. Yeah, but I'm gonna kind of go back here just because I like it that way. So we have 2x equals 0.775 and pi minus 0.775, and I'm wondering, is it possible 2x is equal to something? Remember, these are periodic functions. Is it possible it's equal to something else which might fit in here? That's not. That's true. That's true. Okay, and I'm going to stand on my attempt here to prod you into thinking. I want you to think. Chris, take these papers off. We did this a long time ago, I know, when we first were doing the inverse functions. We had a problem, you know, like this. Say cosine of 3 theta equals 0.5, let's say. We definitely did this stuff. There are more solutions here, but you have to think a little. Where am I going to find those other solutions?
Would you use pi plus 0.775 and divide by 2?
Pi plus 0.775 and do what?
Divide by 2.
Well, okay, these are the inverse of 0.7, right? So why don't we see if the sine of pi plus 0.775 is 0.7?
Okay.
Sine of pi, something you could do during a wizard test. Oh no, it's the sine of this is negative 0.6997. So no, that doesn't sound like it's. Yeah.
How about adding 2 pi here?
What do you want to add 2 pi to?
This is when we say arc sine.
Why do you want to have 2 pi's? It's okay to be wrong, you know. I mean, you could make a mistake, right?
Not really. It's not really a word.
0.775. Well, we should try that, shouldn't we?
But they don't count.
Have a calculator.
And we do it.
Did 2 pi plus 0.775 work? Did 2 pi plus 0.775 work? No, it's because it's outside 2 pi.
I haven't done 2 pi yet. I've done pi plus 0.775.
Pi didn't work?
No, it didn't. I got a negative 0.7 or something.
This is plus 0.7.
Use that on
Two pi
A and B are identical. First
plus 0.775. Oh, that's, I get 0.6997, which rounded is 0.7.
I'm confused, but you did?
0.775.
Yeah, I just added 2 pi to this guy, right? I mean, when I'm finding the inverse sine of something, every 2 pi, right? Sine is periodic every 2 pi, so I'm going to get another answer.
Isn't that 2 pi, isn't that still 2 pi plus 0.775?
It's 2 pi plus 0.775.
But wouldn't that make it greater than 2 pi?
Yes.
We have a restriction.
Yes, it does. Now focus on the question.
We're solving
The question is solutions where sine of 2x is this, right?
So right now you have 2x.
And this is just the sine of, I'm sorry. We're looking for solutions to 2 sine x cosine x equal 0.7, right? And that's sine of 2x. So we just need an x where this is true. This is 1, right? This is 1 also. This is, notice, if this is 2x, sine of that 2x is 0.7. But as you say, this number is outside of 2 pi. But I'm not looking for 2x between 0 and 2 pi. I'm looking for x
Okay, so
between.
it's just all of that.
So I get to divide each of these by 2. There's another one.
Yeah, it would be pi minus, or 3 pi minus.
3 pi minus 0.77.
It's just 2 pi recurring.
And these are each 2x. So if I want to make them x, I divide each of them by 2. And now I have all 4 solutions. If instead of a 2 here, I had a 3 here, how many solutions do you think we might have?
You have
6.
tangent of
What if I went the other way? What if I said like x over 2? That's probably going to reduce the number of answers, right? I'd only expect 1.
equal to 1 divided by tangent.
And if I got really crazy and I said
This is equal to
How about
1
like,
divided by tangent.
5/6x.
Oh,
Now, let's say
this is
let's
equivalent
say
to upper root
1/6x.
1.
We still probably have an answer, but
Tangent
maybe
equal
we'll
to
have
sine
none.
cosine, right? So
we'll
1
have to see.
over cosine.
Okay.
This is equal to 1 over 1.
All right, that was.
Divided by.
I'm glad we did that because again, I think there's a little misunderstanding when it says I want all the answers between 0 and 2 pi. What does that mean? It means there might be more than one.
It's obviously cosine.
So, a comment about some of these problems. I think they're good mental exercises, but not necessarily good math problems, and I'll tell you why. Here's an example. They say use the sum to product identities to find the exact. See, they don't even like let you work your way through that list yourself. Use the sum to product identities to find the exact value of each expression. So here's one. Sine of 11 pi over 12 minus sine of minus 5 pi over 12. Okay, so sum to products. So since we're not like trying to memorize all these, we just take a look at our sheets. And we see, oh, kind of over in the corner here, here's one of these. And then they give you a little formula you can use. 2 sine of theta minus phi, 2 times cosine of theta minus phi over 2. And then you plug in the numbers and you get an exact value. So I'll tell you why I don't, in retrospect, I don't really like these kinds of problems. What we're really setting you up here for with all these identities is those of you who go on and take calculus, invariably when you're doing calculus, you end up with some trigonometric expression. And by itself, it doesn't do you any good. But if you simplify it, suddenly a nice solution pops out. The reason I'm a little raw on these things is I've never seen them come up. I mean, just, so it's a good exercise in, just like a lot of algebra problems are like that. You learn how to manipulate things and then you get good at manipulating them. You get practiced at it, and then when something new comes along, you're not thrown by it. You say, well, let's juggle things around and see what happens. But again, I don't recall any example in calculus where you're doing some differentiation and you're doing some integration and oh, it's the sum to product formula. I mean, it's good to know they're there in case they do come. Okay. All right. Last chance. Any of these other problems that anyone has any issue with? Or I guess you get another chance on Tuesday before the quiz. So, okay.
We have a quiz this Tuesday?
Mm-hmm. Yep.
On identities?
On identities.
Okay.
We keep going back and forth.
So we
Now it's too warm for this. Yep.
So we can use it.
Yes.
Okay.
Yes. Let me repeat that, because apparently I wasn't clear enough. This is a cheat sheet for the quiz and for the exam. I will tell you that you really should memorize the Pythagorean identity. And you should memorize the sum.
Can we use this on the quiz?
Yes. Yes, that's what I'm saying. Yes. Yeah, you should learn the Pythagorean and I'll just write them. I'm not making you memorize them. I'm just saying in your future life as someone who needs some math, sine of x plus y, cosine of x plus y, sine x, cosine y, plus cosine of x, sine y. And this one is cosine x, cosine y, minus sine x, sine y. Now, I mentioned these two because, I don't know if you remember, we kind of presented them
last Tuesday, and we kind of pulled a lot of stuff out. Like, it's real easy to say, well, what happens if this is a minus? Well, if the y is minus, cosine of minus y, it's just the same as cosine of y, so this stays the same. But the sine of minus y, that's an odd function, so this becomes a plus. So you can use that. It's also real easy to use this to say, well, what's the sine of 2x? Well, you plug x in here twice, right? You're just going to get 2 sine x cosine x. And likewise here, you get cosine squared minus sine squared. You know, you want to limit what you have to memorize, right, to your advantage. If you memorize just these, well, these two, and all that other stuff is really easy to pull out.
Right, because let's look at this fraction. 10 over 10. That's equal to 1, right?
And you know, the rest, you know, they'll be in some book somewhere when you need them. Okay, all right, that's it for trig identities, I guess. So we're going to move on.
You have 17x squared over 17x squared.
Okay. The next and last topic for this class is something called a parametric equation. Parametric equations will probably not show up in the first or second quarter of calculus. They probably will show up in the third. Certainly if you do multivariable. We're going to start with an example here. I have some curve in the xy plane. And usually, I show this curve by some equation in x and y. For example, I might say y equals mx plus b, and you should all recognize what that is.
It's a linear.
It's a line, right? Y-intercept b, slope m. I might write something like this: squared plus y squared equals r squared. That's one of the conic sections of the circle of r squared. Or I might say y equals x squared, and I hope you all will recognize that as a parabola. Now, instead I wrote this way: x equals y squared. Does anyone know what that is? X equals y squared. What curve do I get?
Get a square root curve.
Yeah, almost. You do, but you get more.
Isn't it just reflected?
You know, I can't hear you, but your hand signal is perfect.
It's reflected,
It's
isn't it?
like, it's just a parabola that goes off in the other direction. But why is it we hardly ever see that?
It's not a function.
It's not a function, right? So one of the things parametric equations let us do is have these weird curves, but we get back to functions. And the way we do that is we take a generalized point on the curve, and instead of expressing it as x, function of x, have you seen something like this before? I can just plug in an x, and then that's my y, right? F of x, right? Instead, I have two functions. All right? In this case, we're going to use t. I'm going to tell you why t in just a second. So now each of the coordinates is a function of some third variable, a parameter, right? So this is, I guess I could write this down. This is what we call a parametric equation. Parametric equations. Okay, so let's do an example of one of these to see how that works. So the equations out of the book. Oh, I want to say the reason the book likes to use a t is it has nothing to do with math. It has to do with the way people think. And they want you to think of t as time. So, like, you know, at time 0, the point is over here, and then it's kind of moves over, you know, as t increases and does whatever it does. Right? That's not the curve we're going to do here. So, okay, so let me write down my functions.
So this curve doesn't necessarily have to be a function, does it? This curve doesn't have to be a function. Or
the curve itself may not be a function.
that's why we have a function for
It's
x
going
itself.
to be described by two functions. Yes, I mean, I'm agreeing with you. So my first equation, I'm just going to say x equals t squared minus 3t. I'm just pulling these out of nowhere, just as an example. And y is t minus 1. So, okay, so we want to plot this to see what this thing is. So let's put some values down. T is minus 2. All right, so for...
By x and y you mean f of t and g of t?
Yeah, this is my f of t and this is my g of t.
Okay.
I'm sorry? No. There's a question. Okay, so if t is minus 2, 2 squared is 4, minus a minus 6 is 10. That's my x. And minus 2 minus 1 is minus 3. So I've got a point x10. And minus 3. Okay. This is a little tedious here, but we'll suffer through it once. And we'll find another way to do it that's more fun. Okay, 1 minus a minus 3, that's 4. Minus 1, minus 1, minus 2.
Shouldn't that be a negative 4?
Minus 2 squared is positive. Minus 1 squared is positive 1.
Oh, it's minus 1. Okay,
And
my bad.
minus,
Never mind.
minus 3 is... Okay, so 4 minus 2. 1, 2, 3, 4. Minus 2. And minus... Oh, now we can do 0. Oh, wait a second. I've got my points wrong. And then... what's 0 here?
1 and 1.
0 and negative 1.
I think 0 is 0. Minus 1. So 0 minus... Oh, I'm sorry. I had it right before. Minus 1, minus 2, minus 3. Those are my y's. Okay, moving along. 1. 1 minus 3 is minus 1. Minus 1, 0. So minus 1, 0. Okay. It's not quite clear what's going to happen yet, but it will. So 4 minus 6 is minus 2. oh, this is just going down, all right? And 2 minus 1, oh, that's going up. So, minus 2, 1. And 3. Anybody jumping ahead here? It's 3.
0.
0 and 2. Oh. It doesn't look right. 9 minus 9 is definitely 0. 4 minus 6 is minus 2. 3 minus 1 is 2. All right, I'll just, okay. 4, what's 4 going to be? 16 minus 12 is 4. 3. So, 1, 2, 3, 4. 1, 2, 3. Yeah,
When t equals 1.
this is,
T equals
oh, I mixed them up, didn't I? 0, 2. I'm doing wrong here.
When t equals 1, x equals -2, right?
Equals 1. 1 minus 3 is, oh, here?
No, negative, the x should be -2.
Negative 2.
Should
Oh,
be managed.
negative 2, is that it?
Yeah.
Negative 2, 0? Negative 2. Oh, I'm sorry. Negative 2, 1, right?
Explain how tangent is a slope.
Well, my
Because this is, yeah, why is it
my
not-
guide tells me those numbers are right. So I think I'm not
Right.
graphing something
It's a
properly
slope
here.
here.
So let me try one more time. So negative 2, oh, 10, negative 3, right? 4, negative 2, 0, negative 1. And then negative 2, 0. Then negative 2, 1. Okay, now it's correct.
I'm done with the
All right, I got some point up here.
Okay.
If I say 5, 5 is going to be 25 minus 15 is 10. Oh, it's starting to look symmetric.
Even on function.
And then 5 minus 1 is,
Remember, a function can be odd or even.
okay. So, seems to be doing this. All right. So what does that look like? Looks like a parabola going sideways. It's not a function. Okay, so it would be really nice. It'd be really nice if there's some way to check that. So how would we check that? Well, we could try eliminating t. That won't always work, but we can try that here. This is pretty
What do you mean
simple.
by check that?
Alright, so how would I do that? Well, let's solve this guy for t. So t is equal to,
What are we trying to do though? I'm not following.
what I'm trying to do is, having graphed this, seeing it looks like a parabola, let's see if we can just look at what the equation without the parameter looks like. Maybe that'll confirm.
Oh, okay. You want to make it into a function even though it's not?
Not a function, an equation.
Okay.
Is this even
It
odd?
may be a function, it may not, but that's not our goal. Yeah?
Is this even odd function identities?
No, no. This is not an even function or an odd function. Neither of these are even odd functions. They could be, but these are not. Okay, so I take this equation and I solve for t, and now I'll plug t into that equation, right? So x equals y plus 1 squared minus 3 times y plus 1. And I'm going to FOIL this, y squared plus 2y plus 1 minus 3y minus 3. And finally, what do I get? I get y squared minus y minus 2 equals x. Okay. So what can we say about this?
Where did the t go?
So I solved this equation for t.
Okay.
This is like, having two equations and two unknowns, or 3 and 3 unknowns, except we have two equations and 3 unknowns.
Oh, there you just plugged it in.
We can eliminate one of them.
Okay.
So I solve for t, and now I plug into the other equation for t, what I have, and now I have an equation for the curve. It's not a function, but I've gotten rid of the t. And when I look at this, you should be able to say right away, oh, that's a parabola. It's just a parabola sideways instead of up and down.
Oh, no, it's sideways.
Right?
How would you know it's sideways? If we're looking at that, I would assume it's a normal parabola.
Well, there are two ways. One is, I know that y equals ax squared, plus whatever, is a parabola that looks like this if a is positive, and like this if a is negative. And x equals y squared, or ay squared, is either this way or this way. That's just, we could, that goes back to algebra. We could go do that, but I hope you guys remember. Maybe not. Okay, we haven't quite beaten this thing up enough yet. There's one more thing we're going to do, which is we're going to learn how our calculator will help us do this for us. Okay? So if you have your calculator, or if you don't, maybe you have a neighbor who has one. This will take a minute for it to warm up. So the first thing you want to do on your TI calculator, if you have a TI, is go to your mode. Give it a minute. Okay, everybody see this? Okay, so down here you see function. You may remember function, and you may remember pole, POL for polar. But here's this guy here, par. Par is parameter. All right, we set parameter, and let's go to y equals, but now instead of just y equals, we have x, little t, y, t. So let's try plugging in our guy here. So t squared minus 3t, that's our x.
And our y is t minus 1.
Is it t squared minus 3t, or is it t squared parentheses minus 3t?
I heard the first part.
It's t squared minus 3t.
Yes, t squared minus 3t.
Okay, so for this one, wouldn't you have to put parentheses over between the t squared and then minus 3? Because wouldn't that be like t to the 2 minus 3t?
It's t squared, order of operations should work.
So it should be fine.
It's fine.
You only need to do
I'm not clear, is it that you want me to say t
No, I was just taking
Where-
order of operations.
minus 3t?
Yeah,
Is
like-
that it? Well, that'll work too, but squaring supersedes everything,
Except for
except parentheses. Parentheses, yes. Okay, I'm not sure if I have my windows set up right yet. Probably not. So, I don't have my windows set up. So let's try Zoom 6. Oh, that looks like my graph on the board, doesn't it? But you can see that it gets cut off here. Why is it doing that? Well, go look at the window. My t's are starting at 0 and they're going to, it's like 2 pi. But if I start, let's try the t's at say minus 3. Didn't like that. Minus 3 and plus 3. Oh, there we go. Oh, we didn't go far enough. Okay, so go 6. Okay, there it is. It's a parabola sideways. Okay, so that's those are the main tools for dealing with parametric equations. You can eliminate the variable, you can graph it.
Quick question, what zoom mode are you in on the calculator to get that display?
I said zoom standard.
Okay. Mine doesn't have that little Y and X. Is that just because you have a...
This is an 84 plus, maybe that's why.
That's a plus. I guess you just need to do the updates.
There may be some other parameter here, like mode.
It's possible I don't have the latest.
I think I've seen somewhere there's something where you turn the axis label on and off. Is that in window? No. I don't know where that is.
Oh, okay.
Format? Ah, look at your format. Second format. So if I say coordinate off in a graph,
I did my job then. Ask them a question.
no, that's not it. I don't know. Mysteries of the calculator. Why do I have a y and an x on here? Trace?
It's not a big deal.
Not a big deal. Okay. All right, now there's
Cal has like the most latest one, probably has it.
there's something important here though you should be aware of. Hello. There's something you should be aware of. If you think of this parameter as time, think of this, describing what happens in time. What would you expect to happen if you sped up time or slowed time down? Well, you'd expect the curve to get drawn the same way, but maybe a little faster or a little slower.
What do you mean by that?
Stronger stretch down that kid.
Like a horizontal stretch?
No, not stretched at all, just in time. In other words, let's say this prints a point once a second. So 1, 2, 3, 4, 5, 6, like that. It's going to trace this. But if you speed it up, it's just going to do it faster. 1, 2, 3, 4, 5, 6, 7. It doesn't change the curve.
Does it change the scale?
Which-
Yes.
Oh, okay.
It's not going to change the scale
No.
either.
How would it not? I mean, the scale would have to
So-
increase by units.
So let's say I'm going to take these original equations, and for every t, I'm going to substitute 2t, right?
So the time is going twice as fast?
So x is now going to be equal to
Remember if you divide it?
4t squared, and this will be now minus 6t. Y will be,
But where do you get the 4t from?
well, t squared, if I plug in for each t, 2t, and then I square it, get 2t times 2t.
Oh, because you already squared the 4. Okay, I get it.
4t squared. Okay? So now this is a different parameterization, but let's take a look. What happens if I use these new equations? So for t squared minus 6t, and then down here I'm going to say 2t plus 1, and whoa, it's the same graph. And I don't know if you noticed, it actually did graph it faster. Now, it's also, I guess it's a feature of the way the computer in here works. You may notice this is a little more jaggy. I mean, what he's doing is he's putting in points and then connecting them to lines. He doesn't draw every single point. And so now, because there are fewer points, it's more jagged. That's just, that's just the TI. Mathematically, it's the same curve. Okay. All right. That was so much fun. Wow. I didn't write this. Somebody left it for me. We're going to try. Yeah.
And by the way, time for the break.
Right on. It doesn't stop me.
Let's do it. Just to remind you,
We're having so much fun. Okay. Yeah. Enjoy the weather for a few minutes. Take a break. We'll continue from here. So this is a new parametric equation I want to write. And I'm just going to let you sit and think for a second. What could this be? I'm going to make it easier for you. Instead of using t, you can use any letter for the parameter you want, right? You use theta as a hint. While you're thinking about it, I'm going to enter it into here. I'm not going to press the button yet. Okay, any ideas? Any ideas what this parametric, what the curve is going to be?
Is that tangent?
I'm not dividing sine by cosine. I'm just saying x is the sine and y is the cosine.
Oh, I know. It's going to be 10.
Guesses are okay here.
Is it going to be a line?
It's a good guess, no.
Yeah. I don't like
I think maybe it might be.
All right, is there anybody standing outside who needs to be kicked to get back in there?
Not nearby.
Oh, they're just smoking, they're wasting their lives.
They don't smoke.
They drinking.
Because life,
They
because
can't
life's
think
too
up for
long.
this.
Okay, all right. Okay, so for those who just come in at the last minute, we're trying to figure out what this parametric equation might look like. It's going to be a little dull, but then it's going to get fun, okay? Here we go. Whoa. Oh, I better zoom in on that. Zoom in here. I think I get better zoom square because otherwise you'll get the wrong idea. Check this out.
I don't think you're making
Oh, okay. You do?
Congratulations.
Oh, there it is. Okay, a perfectly formed, well, not so perfectly formed. Everyone see what that
I'm
is?
pretty sure we all have.
It's a circle.
If you want.
Okay.
We go for drinks after.
Now,
Somebody could-
maybe you're a little skeptical because it's kind of a jaggedy circle.
Is it actually a perfect circle in like theory?
Yeah.
Okay.
Well, remember what we did with the t's? We got rid of the t's. This is a little harder to get rid of. But there is a way here, right?
So is theta actually a t?
I said theta because I thought that would
Look more
make you
familiar.
think of- it doesn't matter what you call the parameters.
Okay.
All right, so I'm going to take each of these equations and I'm going to square them and I'm going to add them.
Were you trying to solve for t?
I'm trying to get rid of the t.
Oh, okay. Like you did in the other problem.
Exactly. Now I add these together. Sine squared plus cosine squared, that's 1. Okay, so what do I have? Equation of a circle with radius 1. Okay, so you can do that. You can use trig functions
Could
in
you
your
repeat that?
parameter and dull things happen.
Could you repeat that?
Question. Can you,
Yes.
how did you do that? I'm so lost.
I'm a magician, I did it right.
Yeah, no, that doesn't work for me.
Okay, all right, that's fine. I said, I looked at these and I said, I want to eliminate t.
Right, I get that.
So I thought, well, I thought ahead and I thought, well, sine squared plus cosine squared t will go away. So I squared this, and I squared this, get these, I add them together, I get x squared plus y squared equals sine squared t plus cosine squared t,
But you didn't write any of this,
1.
Can you write it down step by step?
like the teacher?
I'm really sorry, but
It's okay.
We're not magicians.
Not yet.
Forget it.
I like Houdini's better.
Good so far?
Nobody knew Houdini's better.
You
Whoops.
added the two equations together.
Why did you add
I
that?
added this and this together, yes.
Okay.
Right, they're equal, so I can add equals with equals.
And we know they're equal because that's just how.
This is kind of like the definition, right? X
Okay.
is cosine of t, y is cosine. That's how we parameterize
So
it.
it's all part of like one equation. Okay.
So now it's all one equation, which just happens to look exactly like.
I put sine squared t plus cosine squared t equals 1 again. Is that an identity?
It's the number one identity.
Okay.
So
if you don't remember anything else from this class, I want you to remember that sine squared of x plus cosine squared of x is 1.
What's the identity called again?
The Pythagorean identity.
I knew that. Testing it.
And the reason it's called the Pythagorean identity is if you take some angle and a circle with, let's say, radius r. This piece here is what? It's r cosine theta. And this piece is r sine theta. Oh, I have them backwards. This that I'm drawing here is also really good to remember. And if I now use the Pythagorean theorem on this, I get r squared, that's the hypotenuse, is equal to the leg squared, right? R squared sine squared plus r squared cosine squared. And now if I divide by r squared,
You get 1 equals sine squared. I see.
it all kind of fits together, right? Who needs trig when you have Pythagoras? Well, you still need trig. Okay, so I promised it would get a little more fun. So
We're already having so much fun. I don't see how.
First, kind of like some low-grade fun. So what would happen instead of just sine t and cosine t? I said, how about 3 cosine t and 2 sine t. What happened? What did I do to my lovely figure here? I'm looking for a word. It begins with E. That's very good. That's not at all what I was thinking. It's an ellipse. It's an ellipse. Okay, let's try something that's maybe a little... Are there any E people here? Double E? Yeah. So you guys have like an oscilloscope, right? So, I mean, the first time I saw one of these figures was on an oscilloscope. A friend of mine had a father who was he was an electrical engineer. Okay, so here I'm now, I'm elongating in the y direction, but in the x direction I'm going 3 times here. Whoa! Oh, I told you it would be fun. Okay, let's just try and flip that. Let's say 2t. I want to zoom out. Oh, okay. No, I guess that's it. It just looks like a little fish, right? Okay. There's a better one here somewhere. Well, they do in I'll cheat and I'll look it up. It's 3t. Oh no, that's the one. That's the one I showed you. Okay, let's try this. Okay, this is called a, pardon my French pronunciation, Lissajous figure. Named after Mr. or maybe Mrs. Lissajous. You can get these things where
It looks like a strand of DNA.
see if I can remember how to do it.
I was looking for that.
I'm speaking.
Anybody watch The Twilight Zone?
Exciting.
On the beginning of The Twilight Zone, they put an oscilloscope and they have it showing the Lissajous figure.
So is that what you brought the first day of class? Oscilloscope?
A movie? No, the TV show. Let's see.
I think it's oscilloscope.
No, I can't figure out.
Is that what you brought the first day of class?
Okay, one more interesting figure before we have to get to work. So, remember when we were doing polar coordinates? Oh, I'm going to remind you all painfully.
Yeah.
So, what is this the polar coordinate equation of?
A circle at 5.
Yeah.
Polar bear.
Right. So,
Yeah.
if I said R equals, I don't know, say, theta. Anyone remember what that would be? You know, at angle 0, it would be R is 0, so it's just here. And then at, say, angle pi over 4, it would be, the raised would be pi over 4. And then at pi over 2, the raised would be pi over 2. And then all the way over here at pi, it would be pi. And it just get bigger and bigger. Right? So how could we write this as parameterization?
And then the other coordinate is your angle. So if you think of your angle, you just do every single angle with the circle.
Well,
Does that make any sense?
yes,
What did you say, what equation makes it a spiral like that?
I did. Oh, this R equals theta.
R equals theta before the
Yeah.
In polar coordinates.
In polar coordinates, yes. So, R equals, let's see, theta, I'm going to do this backwards, see if it works. Theta times 1, right? So R equals theta times sine squared theta plus cosine squared theta. Right?
Is there really annoying?
Actually, I think what I wanted to do, you know what I wanted to do? I wanted to say R squared equals theta squared. That doesn't really change this, right? So R squared equals theta squared sine squared theta plus theta squared cosine squared theta. So maybe, since I know that according to the Pythagorean theorem, x squared plus y squared equals r squared, maybe x squared plus y squared equals theta squared sine squared plus theta squared cosine squared theta. Or maybe what I want to do is now say x squared equals theta squared cosine squared theta. Seems like I'm pulling this out of thin air. Or I can simplify them. X equals theta cosine theta, y equals theta
cosine theta. Okay, let's give that a try. So I'm gonna, I don't have a theta, I have t. I hope I do this right. T sine theta. Oh. I think I mixed these up. Let me try it the other way. I think I want that to be the sine, that to be the cosine. Well, that didn't work.
What are you trying to get to do? Spiral?
Should be cosine. Oh, I know why. I know why, because so I'm going both directions with my t. Instead I say 0, and let's go to, say, 30. There we go. I guess I have to zoom out. Here we go. Here's my spiral. A little work. Zoom out one more time. Okay, so the pearl of wisdom here is that you can have a fairly complex figure, but you can describe it using these parametric equations simply. You can eliminate the variable to see what the equation of that curve is, and you can graph it.
When you do r equals theta, how come it just doesn't cover the entire board? You're saying we aren't going to define how far out we're going, but every single direction.
Why did it stop?
Why is it a spiral, essentially?
Why is it a spiral?
Mm-hmm.
What I'm saying is show me all points on this graph, this polar graph, right, where r, the radius, is equal to the angle.
Okay, I understand now.
Right? So if you think of, like, let's just take something like here, 135 degrees, which is, I don't know, 3 pi over 4, right? So, okay, 3 pi over 4, there's a point. Why is there a point over here? 3 pi over 4
Because
plus
equivalent.
2 pi,
Mm-hmm.
right? I mean, that's what this angle, you know, all the way around is. Right?
So it's also getting smaller infinitely. It's also getting smaller infinitely, technically, isn't it?
Oh, yeah. As you come in, it's going to approach 0 as a, well, at 0, it is 0, right?
At 0, it's 0 degrees.
Does it approach 0 or is it reach 0?
Okay, so as we get close to 0, right, r gets close to 0. We're using sines and cosines, right? Oh, well, we use these equations. Sorry, this should be sine. The sine of 0 is 0 times 0 is 0. Here, cosine goes to 1, but this goes to 0, so it also, the coordinates go to 0, 0. Okay, so we're not quite done. I'm really interested in the back side of this sheet. You can do the front if you like. But questions 5, 6, and 7, I want you to give them. Oh, that's the one. Oh, I'm glad I didn't do it. You get to do it. All right. 5, 6, and 7. Put your name on it. Take your hand at this. If you run out of time, you can take it home and turn it in as homework. If you're Michael, you're going to find out if your calculator does everything a TI does.
There's so many variables involved.
That's what they say about
Can it do everything a TI does?
Yes.
It makes me really nervous when you use the phone there.
All right. I think the coolest image I've seen is number 7. So I think, but I'm not sure. Oh, we're not doing the first one? No, you don't have to do the first one. But you can. It would be good practice for the quiz. Hey, let me say that in an ominous way. The first 4 problems would be good practice for the quiz. Not enough. I can give you more.
The first one.
So you know how to do it, right? Okay. Calculators, man, they are so finicky. Oh, yes. Oh, that is so good.
So you switch it to first mode, switch it to par. It doesn't matter. Yeah.
Yeah, it's definitely from the Twilight Zone. Okay.
I did the standard and then
Is the language a problem, or I just didn't?
and then you zoomed in further. Oh, that's good.
That's it?
Make it safe.
That's all there is? Yeah.
Oh.
I can tell you how to do 6. I guess we missed that. Maybe that'll come up in a minute.
I did that, yeah.
The camera won't use
You don't have to. You can just put some squiggles that I'll interpret it.
No, it's not.
There is actually a
Point
point.
so small. The first time is the exact value.
You can't possibly find the exact value using a calculator. It's always round. Well, some numbers you can get exact, like 1, a half.
It's just
Yeah. Oh, Stanley.
No,
I asked you, didn't I?
I know. No, I got one. I got one.
You got, oh, okay. If you eliminated T, it's correct.
So what if I eliminated this other way?
I got it.
Why is it up there?
Because it's
Four
four
T, four
I know.
Sometimes one is easier. Like in that first example we did. Yeah, if you try it, solve it. Beyond your favorite.
He just did what? No.
You're supposed to solve. You're supposed to find
Express.
So far, it's using y, and that would be y minus 6 equals t, plug it into 2t.
you get x equals 2y minus 12. Which is the same thing as that.
Yeah,
It's the same thing. You just get the
right.
right. I got the same y minus 12.
Yeah.
What you got?
Oh, you take out the T.
You try to solve this. You try to solve Ooh. Oh.
I didn't see my I won't keep it a secret. I'll wait till the next person comes up and says, I don't know how to do that.
You don't need to solve it. You did solve it. You throw it in there, then x equals more than x equals
You had to do the number six. No. Does anybody know how to do number 6?
Yes.
Do you want to show the class?
Wait, well, you taught me how to do it, right?
That might work.
Yeah. But why will I need to? You know how to do it.
Then mark all that.
What is it again? Y1 minus y2. Oh, y. I have a question. You think the game like having a loop clock and what you're saying? You know, like how they do for playtime. Or just
Very good.
like when you're playing
Okay, I
would assume it was.
Okay,
It's aligned.
I need your attention for about 60 seconds.
What did you do?
Yeah, I think I can do this in 60 seconds. Okay, so let's make up a problem. Let's say you want a line that goes through, oh, let's be mathematical. It goes through point A, B,
What if you read that one?
and it has slope equals M. Okay? So I want to think of some parametric equations. Don't you guys want to listen? So the problem is I have a point AB. I want the line to go through AB. There's my line AB. And it, the line has slope, right? So delta y over delta x equals f. Okay. So here's how I do it. I say x equals y equals. In anticipation, I'll have something to write. Well, x, I know at some point it's a, and y is going to be b at that point, right? I guess you don't know this. It's a linear. It's a line. It's linear. It's got to be linear, right? Right. So let's say I were to add delta x to x and delta y over here. Right? Well then, a plus delta x and b plus delta y, that would be this point over here, right? That would also be on the line. In fact, I could add 2 delta x or 2 delta y or t times delta x or t times delta y. Except I don't have delta x and delta y, I just have m, right? And, well, what if I divided both of these by delta y? I mean by delta x, right? Well, this one becomes 1, so that's just a plus t, and that's m. So, mt. I just move x, t, and I just have to move y, m times t. Right? Because delta x, I move delta x, and I have to move y, delta x, I have to move a delta y, which is just delta x times m. Okay, that was too abstract. Now we'll do it the constructive way. So I have some points, 3, 4, and I want a line going through it that has slope 2. So x equals 3 plus t, y equals 4 plus 2t, the slope times t. That's all. It's really easy. This seems to be, no, this isn't about parametric equations, this is about, remember when we were talking about vectors, and if something's not moving, all the forces have to be in balance. So that's what this problem is, I believe.
What do you need to do? This is near. Okay, then do it
It's actually better, the way you understand. When you understand something, that's always a better way, right, than the way you don't understand it. Right?
Why don't you do a simple function, not what I don't understand?
You have.
Tell me what you mean by a simple function.
You have a point.
These are functions, right?
Yeah.
Right? Like f of t is equal to 3 plus t.
So does this always work? You just take 3 plus t to the line as...
Yeah, that will always work for a line. For a line.
Why don't you just calculate, find what the point
okay.
is. Use y equals It's easy enough to calculate the intersection.
That's the equation that's
It
one.
says it always works for a line.
This is the parametric equation of the line. The assignment was to find the parametric equation of a line. I know you guys can find the equation of a line because you've done that in algebra until it came out here, right? This is how to find a parametric equation. You go over it one more time. Okay. So x and y start at 3, 4.
Where'd you get 3 and 4?
That's the problem. And x is equal to t. That's the point. Well, I'm not doing number 6.
Oh, you're not doing number 6. Okay.
You have to do number 6.
Okay, that's why I got really confused for a
Oh,
second.
okay.
Yeah, you can go on. 3, 4.
Don't anybody that you look. Okay. Okay.
And the same.
If you're using this, you can just solve for those.
We're trying to produce parametric equations.
So we're just trying to produce
For a line that goes to this point, slope, whatever. Well, this isn't the only point. Remember I showed you at the beginning, you know, a t moves faster, you get a different equation? I could do that. Or I could do,
why you can't have that shared.
right, because it's a line, right, with a slope, right? And if you go like this, where you go 3 times, right? One A, and you build
Because you're going to solve for x and so you know, but you know, you have to solve for x equals t, and you know x is equal to t.
You could always use that to parameterize the
It doesn't just equal his way is easy. I don't care how his way. I mean, I see his way works. I don't see why it's
For example, how you. I'm trying to say.
Is that what you're saying? Parametric equation? Yes. So that would be
Getting ready for bumper discs.
It's very
Yeah, we need to queue
start. Well, that's the way you do it. Solve for t, run the equation for t, and then you plug it into the other.
Simplest form. I just plugged that in.
Oh, yeah, yeah.
I already had the equation.
Yeah, that's way better.
X equals a plus b, and y equals b plus c squared. Well, and a and b are the points. Yeah, maybe a point. And obviously.
So that was where a equals, that was
A, so x equals a plus t. It's like pretty cool, right? It's
let's first start with the graph, right?
You want the equation right here? All I know is that he's changing Give us an equation.
Well, that is.
Anyway, we're trying to find. All we know is it works. All we know is it works. This is the parametric version of finding and you just plug in where A and B are just a point, and then obviously slope, and that's what you get. Plug it in, and that's the square version of finding what was it this equation at the end. It's easy to see anyway. I don't know. But you should carve it down. That's really weird.
Is that the only way?
Oh,
Aaron.
What was her name?
Okay, how about X equals?
So for the test, I'm pretty sure this should be a
Yeah, why?
I looked through the book and it's look through the whole class.
Yeah,
See if
no.
it's quiz it down. Write anything down.
No, we took his previous class. Maybe together. No. He's
This parametric way.
Yeah.
He was an just plug in.
Now he's a good teacher.
He is.
Present perfect.
He was a good teacher when we took down the
Yeah, I guess
Right? That's why he's this side, you know, I mean, let's say I say,
I still like that one joke I made.
why?
Yes, they are. They are big.
E squared.
Not everybody go to, sun, which is like southern
X equals something, so this is
that's
Should even it out.
No.
He wears some subject letters.
Yeah.
He has special language.
special language.
And he has special like
So I feel like that one joke I made co plus 0.
squared.
What's co plus 0? I know, it's fucking hate that. Dude, we should really No, it doesn't.
It doesn't work really, right?
I thought you were saying full, not flow. That's so weird. That's faux. I know. That's faux. F-A-U-X.
Shut up.
how should I try?
You know.
You can see it. You can see it.
Trust me, I know. I can tell. I never lived with you last
Now we have this.
See, I just look fucking weirdo. Like, I remember this only time I can next weirdo. Except for my work, I can't. I actually care about what I do. I work in the city. I am a business development manager for a city.
Three.
He's a big.
So now I just made
That's why you have to
now E squared equals 1.
I'm only 38. I act like a 5-year-old.
I'm not saying he ages really well.
I really want to age. He's really well.
Yes.
Plus 1.
I know how from
B is plus 1 and 2A.
No me for the same amount of time.
here is a long time in college.
Yeah, college and he just moved around.
Good, yeah.
Kyle and Kyle were in the same.
Yeah,
I know, right?
We moved after half a year.
Try.
That's fall.
So we
We sat next to each other. Kyle made one.
No.
He is 23 minus 4.
How old are you?
22. I saw 26
Yeah.
for
Oh,
in New York. I was New Year's Day. No, not quite. I was in the. I was for New Year's Day.
Oh.
I was there for work and just it was cool. My feet were freezing.
yeah, I heard that you're not supposed to go to Times Square.
Well, it's only once in your lifetime, and I'm never doing it again.
You have to get like a hotel nearby.
We were in the middle of Orlando, so I thought Carlos was doing that sing that reggae song.
Dude, that same
With
sound.
long hair and white lips.
What song is it? Is it the That's like the white guy who does.
No,
No.
it's like, it's a really popular one.
What's the
Find
song?
a character.
I'm trying to think. Just give me a minute.
Did I look older than 18?
Dun, dun, dun.
I don't know if you can.
does it go? I don't know that song. I don't know. Plenty of record songs. Why do you have to be so? Yeah. How does it go? How does it go? How does the song go? Yes.
It's a fake reggae guy. Jamaican, even though he's white.
You look like last year. She was actually really pretty. I saw her live. I never liked her, but that was because I was so biased. I'm still. But then I saw her. And I was like, how about that? That girl has because she's like a sleeveless or tank or whatever. Sprinkly like whatever tank top. A sleeveless whatever with a sprinkly whatever. I was like, sorry.
No, it was not.
Okay, it was close.
Okay.
It's 32 degrees. Talking about Celsius.
Where's that? Fahrenheit? 20 degrees Fahrenheit?
It's really hot. That's why I got 70-something degrees.
That's Celsius.
Celsius, sorry.
Fahrenheit under 32.
Yeah, it's 0.
It's freezing.
Yeah. So if it's 20
degrees Celsius is going to be around, what, 70?
So you just need to like
Question.
what's 20 degrees Celsius?
20 degrees Celsius is like negative.
Whoa, I don't know. 20 degrees Celsius.
Oh, sorry. Sorry, I was saying Fahrenheit. So 20 negative is like negative 60.
What's the body temperature in Celsius? What's body temperature in Celsius? 38. 90-something. 30? 90?
Temperature.
Fahrenheit's 98.8.
98.8 plus 32.
She's a biology. Okay. No one's in Celsius.
Come on, biomechanics.
Marketing. Special bullshit.
Computer science. Okay, then you are.
Computer science. The bastard.
Silverman.
Engineers.
You have family? Silverman's like van something? What time? Tuesday, Thursday? Okay.
Then it's probably Silverman.
Is it Silverman or van something?
Is it a woman or is it a man?
It is Semlin.
Silverman's a woman.
Silverman was like Friday. Monday was Friday. I want you to Brian for Tuesday, Thursday. And
So we'll be going to that.
yeah, I know, but yeah, something like that. Which would be nice. Because him and I are gonna like walk in during his lecture.
I'm trying to get class.
What if only one
can't get
can accept it after rest?
I will run fast.
You're early enough. The wait list is only 4. Yeah, I know.
Round up.
Besides, he's trying to make me laugh. I have less. SJSU.
There's a certain
You can fail the class if you don't listen up. So,
that's illegal.
while I was typing this in, I made a mistake. Something here is found.
Oh, surprising.
You can all thank him.
Thank you. Oh, thank
You won't fail. If you look
I think you should be a teacher.
at the identity sine theta sine phi,
Could you put it over? Sine theta sine phi. Found it.
Yeah, I don't think it's
you'll notice that that's cosine theta minus phi minus cosine theta minus phi, which is 0. So that can't be right. But if you look in the book, you'll see that I left out a
plus sign here.
Oh, yeah, okay.
So you might want to put that plus sign in.
But you get extra credit.
And you might want to take Jonathan out for a coffee or a beer, you know, because otherwise you could have failed the final.
No.
I'm pretty sure that one's on you. But we don't have to talk about it.
That's not like
Oh, he has another question.
I give him a
Hold the rest.
Okay.
No, you can't make mistakes in the classroom. I was just saying this. And then, just, you know, there's has. And then we can do like this person.
It's not fair.
Oh yeah, my bad.
What he probably would have done is appeared on the final and did correct this. He would have given us, again, he would have given everyone credit.
Yeah, I went to the conference.
Yeah, I thought I wasn't here. That's what everyone thought.
Yeah, me too. I was not part of it. I was using it.
I don't know what this is.
Look at that. That's a Stormtrooper 3D printed. Really? 3D printed. That's huge. That's like my height.
If you have trouble tracing the last one, it's okay. I can't do it.
I don't know.
You just say, I couldn't do this, and I know you got it right.
Oh, it's a certain type of plastic. I don't know. It's like it's hard to. So guys, I'll see you guys later for the group session. Then we can go get the shit face.
When?
Tomorrow.
Drinks after
Is it going to be like an evening? I work until 5.